Okay, this is a video for reviewing ionic bonds and covalent bonds. So this is video part 1 for ionic bonds. We're going to look at noble gas configurations, electron dot diagrams, charges, and things like this. All right, let's take a look at the first slide. What is noble gas configuration for calcium and its electron dot diagram? Once you figure that out, try to determine what charge calcium will make and how many electrons it may gain or lose. So pause the video, take a look at your periodic table, and see if you can figure it out. Okay, now let's assume that you have figured this out and you're looking at it. Okay, and let's see what you've figured out. Okay, I'm just trying to clean it up a little bit for us. Okay, so the noble gas configuration for calcium, let's take a look at the periodic table here. Calcium is located in the 4th row. It's an S2, and it will have 2 dots. But what noble gas would have filled before that? It would have been argon. So there it is right there. So it would be argon 4s2 with 2 dots. So we have argon 4s2 and calcium with 2 dots. Now what about calcium becoming stable? Well, calcium wants to have 8 electrons in its outer level, just like all the other atoms. It only has 2, so it could gain 6 or lose 2. So it's going to choose to lose 2 electrons and become positive 2 in charge. Now why is it positive 2 instead of negative 2? Well, remember, electrons are negative, so if you lose something that is negative, okay, it'll make a positive charge. So we have a positive 2 charge there. So hopefully that makes good sense. Now let's try something else. Same thing. What's the noble gas configuration for chlorine? What's its dot diagrams? What charge will it become? And after that, try to figure out the chemical formula between calcium and chlorine. All right, pause the video, see if you can figure all that out. Okay, assuming that you have paused the video, let's take a look at the noble gas configuration. Going for chlorine here, we're located right here. We're in the P5, and we're in the 3rd row of the periodic table, so we know we're a 3P5, and we have a 3S2. Remember, you got to fill the S2 first, and then the P5. And then we go, what noble gas do we have? That would be neon. Okay, so chlorine would then be neon 3S2, 3P5 for its noble gas configuration, and it's in the group 17, okay, which has 7 dots in its outer level. So let's go back to that. So we have neon 3s2 3p5. It has 7 dots. Now chlorine wants to become stable, so it could either lose 7 electrons or simply gain 1. So it's going to take the quicker route. It's just going to gain 1 electron. Now electrons are negative in charge, so when they're negative in charge, because they were determined that by the J.J. Thomson experiment. So if that's true, if chlorine gains 1 electron, then it'll be negative 1 in charge. So what's the formula for calcium chloride? Remember before, what we did is we wrote calcium positive 2, chloride minus 1, and then we would crisscross the charges. So therefore a 2 would go down here and a 1 would go down there. So that would be the chemical formula for calcium chloride. What about the reaction between calcium metal, okay, and chlorine gas? Well, let's take a look. So here's calcium metal. This is calcium Ca with its 2 dots on it. And this is chlorine gas, Cl. It has 7 dots on it like this. It's a green gas, very toxic gas. Calcium metal is very silver, and it's a soft metal, similar to sodium that we demonstrated in class, except a little harder. When you heat up calcium metal and react it with chlorine gas in some kind of a beaker or a chamber, this is the reaction you see. An electron transfer process is going to happen. The end result is a calcium chloride compound, a white crystal. And that crystal is, you might have seen this in the wintertime when people spread salt out on their sidewalks. This is a special kind of salt, calcium chloride. This is the white pellets. Most people just put sodium chloride out there, but this is calcium chloride. It turns out it melts ice a little bit better. Okay, so, but what's happening in this reaction here? Well, calcium is now donating its electrons over to chlorine. Okay, Now we see, oh, calcium's got one more electron left over, so then we have a Cl again. I will draw that like this. And we can draw the electron going across to this one. Notice how I'm being specific. I'm drawing the electron leaving from one place over to a specific location here, okay, and there where there's only one dot on the chlorine. Then we write calcium has a positive 2 charge, and chlorine's got a -1 charge. So this process is shown right here where you see the chemical reaction actually happening right before your very eyes. Okay, so that's the calcium chloride reaction there. So what does it look like, okay, when we're done? Well, the crystal structure, that white powder stuff you saw there, looks like this. So what holds this crystal together? Well, if calcium is positive and chlorine is minus, those are opposite charges, and opposite charges attract. So once the reaction's done, these crystal structures form because of that attraction. What are we looking at here? These small ones are the calcium, +2. These green ones here are the chlorides. And we see that there's some kind of alternating pattern between positive, negative, positive, negative, positive, negative. And that crystal lattice structure develops. Now this, of course, is a very blown up version, okay, of that crystal lattice structure. And you're not asked to know all the crystal lattice structures for all the compounds. I just want you to understand that this is what happens for ionic compounds. Those crystal lattice structures are very, very strong, and they have very high melting temperatures, maybe 500 degrees Celsius, 1,000 degrees Celsius, something really, really hot in order to melt those, because those ionic bonds are so strong, those opposite attractions that we see. Okay, I want you now to try 4 of the diagrams for drawing, okay, that we've done before. I want you to review those. So pause the video now and make an attempt, use your periodic table, and show the ionic bond process happening, okay, with the arrows as they go across. Okay, now assuming that you have tried all of these and paused the video, here's our answers. For aluminum, it's a +3. So in fluoride's a -1. How do we get that? Well, there's 3 dots on aluminum, and I'm going to show electrons transferring over to the fluorines. Each fluorine has 7 dots, and there should be 1 dot left open for those electrons to transfer over to. So this is AlF3. Now we can put a +3 because if aluminum loses 3 electrons, it'll become +3. So here goes. All right, +3, and then the fluorines each gain -1. So then I can crisscross charges. So what this means is there should be 3 fluorines for every 1 aluminum, and that's exactly what we've drawn here. Now what about potassium phosphate? Well, each one of the potassiums have 1 dot, phosphorus has 3 dots, so again I'm showing 1 electron going over to each of the phosphoruses. Therefore, there would be a +1 on each potassium, and each phosphorus would gain a -3 charge. And we write that up there, K +1, P -3. We would crisscross charges. There would be 3 potassiums for every 1 phosphorus atom. And down here, the magnesium nitride. Magnesium each has 2 dots. Nitrogen has 5 dots, so there are 3 spaces where I can transfer electrons across. Each magnesium gives up 2 of its electrons as we transfer them across. Okay, and if you think about it, there's 6 total electrons transferred across. And if we look at our charges, we have a +2 and a -3. Our least common denominator between those two is going to be 6. What do? We crisscross charges. A +2, the 2 goes down there, and 3 goes down there. Remember, we don't bring negatives or positives down. We just crisscross charges. This means there's 3 magnesiums for every 2 nitrogen atoms. And lastly, calcium sulfide. We've got 2 dots for the calcium here, and sulfur has 6 dots. So there are 2 places for them to go across. 1 electron goes from this calcium to that sulfur. 1 electron from the calcium over here goes to the same sulfur. And then therefore we have calcium +2, sulfur -2. So calcium lost 2, sulfur gains 2. Now what we would do here is we'd have a calcium +2, sulfur -2. We would crisscross charges, and you would notice that we have a 2 and a 2. What we do there is we simplify. Remember, our process is crisscross the charges and simplify. Since 2 and a 2 are both divisible by 2, we would be left with 1 and 1. And what that means is there's 1 calcium for every 1 sulfur atom. Okay, that'll do it for our ionic bonding review. Covalent bonding review will be next.